Hi, I'm Erroll, a scientist at Microsoft Cambridge, UK. And today my colleague Tadas and I are going to be talking to you about how we create synthetic data for human-related computer vision problems. And first, we're going to focus on how synthetics brought hand tracking on HoloLens 2 to life. So hopefully, many of you by now will have been fortunate enough to experience the magic of hand tracking on HoloLens 2. So for the first time, users can simply interact with virtual objects much like they would do in the real world by reaching out and touching them. And this is made possible with fully articulated hand tracking. So here's a debugging view of our hand tracking algorithm running on HoloLens 2. Hand tracking relies on model fitting and sophisticated machine learning for per pixel segmentation and key point localization. And that's what you can see at the bottom there. And what you might find surprising is that these neural networks were trained with synthetic data only. So they never saw a single real image during training. So what do I mean by synthetic data? I mean labeled images made using computer graphics. And for me, the three most important benefits of synthetic data are as follows. Firstly, you can guarantee yourself clean labels without annotation noise or error. Secondly, you can generate labels that are otherwise impossible to annotate by hand. And finally, it's easy to control variation in your dataset. So let's have a look at some of the synthetic data we used for HoloLens 2. So I hope you agree this looks pretty realistic. So on the left, you can see a visible light image. And in the middle, you can see a simulated depth camera image. And finally, on the right, you can see some example labels we use for machine learning. So everything here is computer graphics, it's all rendered. So as you know, HoloLens has a time-of-flight depth camera, and we actually simulated its operation exactly. So we simulated every pulse of light bouncing around the scene and ran the exact raw to depth algorithms to generate depth, just like what happens in HoloLens 2. But we simulated the light using a ray tracing renderer. And this is how we get just the exact same types of artifacts we see in the real world in our simulated depth images, like really shiny objects become invalid, and fast-moving objects can be invalidated, and so on. And on the machine learning label side of things, you can see here are labels for part segmentation, but we also have labels for key points or dense correspondences. And these labels enabled the machine learning that made hand tracking work. So what makes good synthetic data? In my opinion, there are sort of three dimensions that are most important, and they are realism, diversity, and richness of label. And of course, what we want is synthetic data that is super realistic, super diverse, and has the best labels possible. So let's talk about each one of these in turn. So first, let's talk about realism. And in many ways, and in my opinion, this is the most important thing to get right. So I always want to be all the way down on the right side of this line. And so, people have found success with less realistic data, and that's great. But I always worry about the potential domain mismatch from going from synthetic to real. So if your data is photorealistic, you will not have a domain mismatch. You can make data, synthetic data, that is indistinguishable from real data. And there is no reason why this can't be possible with good enough computer graphics. So the worry is, otherwise we'll train a neural network and it will work sometimes and it won't work in other times. And you want to avoid this kind of situation where you're worrying that your data isn't realistic enough, and that's why it's not working. You want to be in a situation where you can always make realistic data and you can debug problems that come from other avenues. Now let's talk about diversity. So for training data to generalize to the real world in the wild scenarios, it should represent the diversity of humanity. So humans, look really different from one another, both in their size and shape, and in the clothes and accessories they choose to wear. So on the one end of the spectrum, it might be easy enough to create synthetic data that handles the most common cases very well. For example, people wearing t-shirts and jeans. And from a computer graphics perspective, these clothes are some of the easiest to render and animate. But human diversity has a very long tail. And if you want your machine learning to generalize to, the Eurovision end of the spectrum, you need to make a serious investment in clothing diversity. And finally, richness of label. So there are many human-related problems in computer vision, and they all require different types of label. And sometimes coarse labels are sufficient. So these are like bounding boxes, or maybe even, foreground, background labels. But sometimes you want much richer labels. For example, really accurate skeletal joints that you see through an object, or dense surface correspondences. And it's these kind of problems that synthetics can unlock. So with synthetics, when you do a render, you can get this kind of label for free. So these are the kind of labels that are impossible or extremely, extremely expensive for a human to annotate accurately. So how do you make good synthetic data? So I think the first thing to realize is that synthetics is visual effects. So sometimes in the literature, synthetics is used as a toy problem, but on the other end of the spectrum, like if you do it right and at scale, it's visual effects much like a Hollywood movie. However, we've got to remember that for us, diversity is super important. So with a Hollywood movie, you might be rendering a few hundred different shots of a handful of important characters or actors, but for us, for maximum diversity, we want every single frame to be as different as possible from one another. So you want to render, 100,000 different people or something. So unless you have a massive production house of artists that can prepare 100,000 different shots of different people, you'll need to do this procedurally. And so how do we do that? And so this is my approach. And so first of all, it starts with a super good parametric 3D model of a human or part of a human. And so luckily for us, it's possible, I think, to parameterize human beings and, given a 3D mesh and parameters to this model, you can create any sort of human or naked human. Now, it's not enough to generate static humans, people move around. So you also need a comprehensive and diverse body pose database that covers your target scenarios. And then, another part, a key part of human diversity is what we wear. And so you need a digital wardrobe from which to dress up your digital subjects. And finally, last but not least, you need something to render your humans with. So for me, the most, the foundation of this approach and the most important thing is the parametric model. So let's have a look at ours for hand tracking. So this is what it looks like, this blue mesh here. And this is a reasonably traditional rigged model. It's a mesh with some joints in it. And the shape of the mesh and the locations of the joints were learned in a large machine learning process involving a lot of hand scan data. And so this mesh is what we use to track hands in HoloLens 2, but it's not very realistic. So we also have a realistic version which has been retopologized, and we have a collection of realistic hand textures that we can use for rendering. So it's, our hand model let us know about how hands change in shape, but we also need to learn about how they move. So for this, we captured a massive pose database using markerless motion capture technology. And in fact, this was building upon the same sort of technology you see used in holoportation or mixed reality capture studios. And so this gave us a lot of 3D point cloud data of various hand poses. And that's what the red pixels you can see in this capture are here. So these are 3D points. They're not hand poses yet. So we turn these 3D points into parameters for a hand model using model fitting. So this is using the same sort of algorithm we run in HoloLens 2, but in the cloud at a massive scale. So given around 300,000 data points, we run this cloud-powered, beefed-up version of our model fitter and fit our hand model to the data offline, getting really accurate and robust hand poses. And this gives us our pose database. And so then we apply our digital wardrobe. So here you can see a selection of different sleeves, watches, and rings. And this reminds me of a funny story actually during HoloLens 2 development. So at the beginning, when we were training our machine learning models, it was the summertime, and it was nice and hot, and everyone was wearing t-shirts, and everything was working great. And then it started getting colder, and people started wearing longer sleeve clothing, and the machine learning started breaking, and we realized, of course, we don't have any sleeves in our training data. So this summer data was no longer very useful, and we needed to increase our digital wardrobe. But that's the sort of thing that isn't too hard with synthetics and a team of artists. You can prepare these sorts of clothing items and accessories. And so finally, you mix it all together. You mix all your different hand shapes, hand poses, sleeves, watches, rings, and render everything. And unfortunately, this part is still a bit like alchemy. It's pretty hard to know how to get the mix right. How many poses to mix in here, and what proportion of sleeves or that sort of thing. And so what's really important is to have a tight render and train pipeline. You've got to be able to iterate quickly and have a real test set to measure your performance against to figure out what's working and what's not. Here's some more examples actually of the data we used in a sort of test scene. And what you might notice here, how it's different from the video I showed earlier, is like the rest of the body's disappeared. And I think the lesson here is that it's important to do the effects for the shot you need. So we realized that for the machine learning models we wanted to train, we didn't need to have the whole body, and it was a real nightmare getting the whole body to work with the hand poses from a parametric hand model. We did this thing called this like hand model transplant, where we chopped the hands off the original like full bodies and we tried to put our own hand models on, and it worked, maybe 95% of the time, but then weird things would happen where like hands would pop off or something. So we said we just get rid of the whole body, focus just on this part of the hand and the sleeves and watches and stuff. And it made our life a lot easier, and it allowed us to improve realism just for one small part of the human, just the hand and the wrists and the forearm, even though you're sacrificing realism at another scale. So it's not quite so straightforward as you can only go one direction on the realism spectrum. Sometimes it's a compromise, right? You in order to achieve the shot you require, you say I will sacrifice something somewhere else. So once you have a fully functional synthetic pipeline, you'll start to realize that synthetic data isn't just as good as real data. In fact, it can be better than real data. So synthetics allows you to easily solve tasks you would never attempt with real data. For example, here, per pixel dense correspondence estimation, or dense 2D key point estimation. So these, by the way, aren't used in HoloLens 2. These were just experiments performed during its development. But these models would have been impossible to train with human annotated data, probably. But with synthetics, it was easy enough. Okay, so here you can see the dense 2D key points. So this is the same machine learning algorithm that we use to predict 9 key points as we do in HoloLens, but just trained with 500 key points instead, and it worked okay in the end. And it was very, very easy to get this kind of label data with synthetics. And so that was hand tracking. So now I'd love to hand you over to my colleague Tadas, who's going to talk about what we've worked on since then, face synthetics.
Thanks for that great overview of synthetic data and how it was used to train hand tracking models for HoloLens 2, Erroll. And I'm Tadas Baltrusaitis. I'm also a scientist in Microsoft Cambridge. And today I'll be talking about our face synthetics pipeline and how we use it to generate data for training machine learning models related to faces. So let's jump straight into showing some of the images we can generate using our synthetic framework. So here on the left, you can see images rendered using our face synthetics framework, together with annotations corresponding to those images on the right. So annotations for facial landmarks, for face normals, for segmentation masks. And I hope that you'll agree that these images look very realistic and will also demonstrate that they are realistic enough to train machine learning models that will perform on real data. So let's jump in to explaining how we generate images like this. So as Erroll mentioned, as we do for hands, we have a procedural generation pipeline that relies on a parametric model of a face. It relies on a texture library, a hair library, and a digital wardrobe. And then finally, we place the face in an environment and provide some illumination to it. So let's talk about our parametric face model. It is reasonably straightforward, linear parametric model that is trained on about 500 diverse scans of people that were retopologized to align them to a common topology, and that we can sample to get unseen faces. And here in this image, you can see a number of faces sampled from our parametric face model. So none of these people actually exist. And you can see that our model manages to capture diversity reasonably well, managing to capture different ages, gender, and ethnicities. Um, in addition to an identity model, we also have an expression model, which is handcrafted by an artist with over 200 blend shapes. Again, it's a linear model with addition of bones to control head motion and eye motion, eye rotation. So just having ability to sample identity is not enough. We also want to sample expressions. So how do we do that? Similarly to hands, we also have a multiple camera capture rig to capture facial performance. It's a markerless capture system that we detect facial landmarks from the image streams and perform model fitting to get that. So to get at the mocap data of facial expressions. So here on the right, you see some examples of such mocap data. So we capture things like head pose, blend shapes that describe facial expression, and eye gaze information as well. So, and then we can use that to replay in our synthetic pipeline. Now, uh, we need to, in addition to having identity and expression, we also need to add texture to our model. So for that, we use exemplar-based texture models. So we have a couple of hundred scans that were processed that we baked albedos from. And we can't just use directly the baked albedos from these scans. We actually had to manually clean them up to remove things like noise, like facial hair, hair nets, because we don't want them baked into our texture. We want to be able to control them, to sample them independently. So this allows us to get a very high quality texture library. In addition to having albedo textures, we also have displacement textures that were built from this scan data as well. This allows us to capture things like wrinkling that our parametric model is not able to capture because it's not high enough resolution. In addition to meso displacement, we also have micro displacement textures, which allow us to capture things like pore level detail. So you can see it in the image on the right here. And with our sort of meso and micro displacement maps and albedo combined, you get the sort of the full textured face model. So we don't want naked heads floating in space. We also want to add hair to them. And for that, we use a strand-based hair model where each hair strand is modeled individually. And some of our hair assets can have over 100,000 strands to represent them, especially sort of more curly or really long hair grooms. And we have a big library of eyebrows, facial hair, head hair, and eyelashes. And each of the grooms was authored by an expert hair artist in Maya's XGen. And we choose, when sampling a head, we choose randomly from one of these hairstyles and mix and match various head hairs and facial hairs and eyebrows and eyelashes. And in here in the figure, you can see some examples of that. In addition to sampling the hair shape, we also sample hair materials to allow for things like different hair color, different hair shininess or roughness, uh, ability to sample gray hair or even dyed hair, dyed or bleached hair. So, and the fact that we're modeling our hair as strands allows us to capture really nice illumination effects if there's light behind hair or or light shining through hair. So this allows us to capture this extra level of realism. So in addition to hair, we also have a digital wardrobe. So it is an artist created wardrobe of upper body clothing of headwear, such as helmets or headphones, facewear, such as face masks or even eye patches, and eyeglasses. So the artists created all the items of clothing on a base head, so we need to adapt it to different face shapes. So we use lattice deformer to do that, with additional shrink wrap elements to cope with certain, sometimes skin sticking out of the items of clothing, and this sort of using typical visual effects or computer graphics tricks to make it work and to sort of put the scene together. In addition, for eyeglasses, we also have a rig, with a skeleton rig that allows us to pose glasses on different heads, so that they sit on your ears and on the nose ridge, so that the glasses adapt to different shaped heads. To expand the diversity of our digital wardrobe, because you can only craft so many items of clothing. For example, in our library, we have 30 items of clothing. We also create procedural materials to allow us to sort of create extra diversity without authoring new items of clothing every time. So these materials allow us to vary color of the clothes, allow us to vary patterns, going from stripes to checks to uniform patterns or different textures. They also allow us to vary the material, so going from something like suede to leather. And having this very extra sort of proceduralism reduces the chance of seeing the same item of clothing, the exact same item of clothing, twice in your big rendered data set, which is really important when generating synthetic data. So here's another example of sampling from our digital wardrobe. You can see different types of assets we have, ranging from helmets, hats, headscarves, religious headwear, upper body clothing, and different types of glasses. And you can see sort of the high diversity there. So once we've assembled the head, added hair to it, added texture and clothing to it, we need to place it in a scene. So and we need to illuminate it. So for that, we use high dynamic range images. So they provide both illumination and the background scene, so which is quite nice, and background scene that is sort of consistent with the illumination. So here in the video, you can see different HDRIs we use, and them being rotated to see sort of how much the illumination affects the variability of the image. So even being placed in the same scene, but just rotating the HDRI changes drastically differently looking faces. And here's another example on the right, where the same face is illuminated with different HDRIs, and you can see this stark difference. And you can get a lot of diversity, even if your sort of expression or identity library is not as diverse, just from varying the illumination. It's a very sort of strong, it's a technique that has sort of a lot of applications. Okay, so now that we've assembled the face and illuminated it, placed it in an environment, it's time to render it. So we use Blender Cycles Renderer for our face synthetics work. It is a physically based path tracer, and instrumenting it also allows us to generate ground truth annotations to accompany these renders. Things like segmentation masks, normals, or landmarks. And specifically for today, I'll be focusing on the segmentation and the landmark side of it. And we render big data sets on Azure clusters. So let's talk about a particular example of a data set and downstream task we evaluated it on. So we rendered a 100,000 image dataset of 512 by 512 pixel images with accompanying annotations for facial landmarks and segmentation masks. And we sampled each asset type that I've already described independently. So sampled identity, expression, hair, clothing, illumination, and environment independently for greatest variability. And in addition to that, we also sampled different camera locations, rotations, focal lengths, depth of field to also create extra variability. And this allowed us to render a 100,000 image dataset. A sample from that dataset can be seen here. That you can see that there's a lot of variability in appearance of individuals. So this allows us to create datasets that generalize to real data and that capture a lot of sort of diversity and that we expect to generalize not only to simple images from real data, but also to complex scenes as well. So here's an example of that type of generalization. So if you use only synthetic data for training, similar to Hans' case, and we take an off-the-shelf ResNet 34 neural network to predict 669 landmark locations directly. So a dense landmark set. And you can see example predictions on the video on the bottom left and some images from the 300W test set on the right. And you can see that our model is able to generalize really well to quite complex scenes from that data set. One thing that is worth mentioning is that because our render process generates images from a perfect camera, from a perfect pinhole camera without any sensor noise, we use a lot of augmentation during training time. So we perform things like gamma correction, adding shot noise, motion blur, Gaussian blur, vary contrast, of the image, and also do a lot of sort of geometric transforms such as perspective transforms, various warping, shifting, scaling, and rotating of images to generate this extra diversity, and meaning that our neural network, when it's being trained, is never going to see the same image twice. So this is quite important when using synthetic data, but also when using real data too. The augmentations plays quite an important role. So here's another example of using synthetic data for training a sparse landmark detector. So this is using a standard 68 landmark annotation set. So here's an example of it generalizing to images from 300W dataset and on a video and on a stock video. So a lot of you might be sort of asking sort of how big does your synthetic training data set have to be for it to generalize well? And this is a question we've been asking ourselves and did an experiment to sort of to investigate that as well. And we evaluated on real test sets from 300W landmark detection challenge. And we found that you start getting about diminishing returns after 50,000 images, at least on the type of data we generated. You might still get a slight boost on certain subsets with 100,000 images, but the returns are quite diminishing. So it seems like 50,000 images lead to quite good results. So going on to a next example of face segmentation. So we also evaluated our networks on a face, sometimes called face parsing task as well. So when training purely again on synthetic data without the model ever seeing a real image and using an off-the-shelf UNet with a ResNet 18 encoder, we are able to train face segmentation networks. And here are some examples of them performing on real data. So I especially like how well it is able to get strands of hair, which are typically not annotated on real data because it's just too difficult for a human to annotate pixel perfectly annotate images of real data and getting each hair strand individually. Whereas when using synthetic data, we can get that automatically, which is really nice. And another example of generalizing to different style of data. So because our face model is such high fidelity and all of our assets are of high quality, we're able to render images from really up close. And here's examples of images rendered from a camera really up close next to the eye, similar to cameras that could be used for eye tracking. And on the left, you can see synthetic training data, and on the right, you can see a segmentation network trained purely on synthetic data generalizing on real data, uh, even when a person is wearing glasses, for example. So hopefully this has convinced you of the usefulness of synthetic data and of the power in synthetic data generation, which, as Erroll already mentioned, sometimes is not just as good as real data, but often is better. And I want to conclude with a sort of small teaser of what's next for us. So whilst we focused on faces and hands, and we still have this dream of building a human synthetics pipeline that would allow us to render everything together at really high fidelity, in a sort of one unified system. And here's a sort of small teaser of some of the work we've been doing in that direction. And yeah, thank you for your attention.